Okay, I'm going to run through the travelling salesperson problem all the way through. Okay. Now notice how the travelling salesperson problem isn't called the travelling salesperson algorithm. That is because there is no such algorithm. There is no best way to find a Hamiltonian cycle that is the minimum. What we can do, however, is we can split the problem into a lower bound, the lower bound algorithm, okay, conveniently titled, and an upper bound from the nearest neighbour algorithm. And our optimal solution, okay, the best solution that we can possibly find, is somewhere between the two. Okay, so the lower bound is less than or equal to the optimal solution, which is less than or equal to the upper bound. If, for example, you found the lower bound to be 20 and the upper bound was 20 as well, then the optimal solution will have a value of 20. Okay, and a possible Hamiltonian cycle for this will be given by the nearest neighbour algorithm. Okay, so notice how this is a problem involving a Hamiltonian cycle, while the Chinese postman algorithm from chapter 6 was all to do with Eulerian cycles. Okay, right. This is the graph that I'm going to work with for the lower bound algorithm. Okay, and how it works is I start off by deleting one of the vertices. Now, you will usually be told in the exam which one you should delete. Okay, so say I was going to delete A. Okay, so in other words, what I've got to do is I've got to not delete A, but ignore A for the time being, and I am going to find the minimum spanning tree for the remaining 4 vertices. Okay, so let's see what we get. So for the minimum spanning tree, of course, we've got 2 methods for that. We've either got Kruskal's or we've got prims. Okay, so in this example, I think what I'll do is I'll use Kruskal's. So first off, I've got BC, so we've got to list the edges in order of weight. Okay, so BC has weight 1. We've also got BD of weight 2. We've also got CE of weight 2. We've got ED of weight 4. DC of weight 5. And BE of weight 6. Okay, so they are the 6 edges that we have remaining when we get rid of A, because when we get rid of A, all the edges coming out of A are got rid of as well. Okay, so what I'm going to do is I'm going to have a look at each one in turn. BC, okay, so I'm going to add that one in. I'll have that one. BD, I can add that one in. It won't add it. It won't make a cycle. CE, I can add that one in because that won't make a cycle. Now all 4 vertices are connected by edges, so I don't need to consider ED, DC or BE. Okay, so now that I've got that, the last thing you do in the lower bound algorithm is you add back in the two shortest edges coming out of A. In this case, that's AB at 1 and AE at 2. Okay, so I will write those down. We've added back in AB of 1 and AE of weight 2. So the total weight of this minimum connector in this case is 1 plus 2 plus 2 plus 1 plus 2. So 3, 4, 5, 6, 7, 8. Okay, so the lower bound algorithm has given us a lower bound value for the Hamiltonian cycle for the optimal solution at 8. Okay. So now I'm going to consider the nearest neighbour algorithm, which is going to give us an upper bound. The nearest neighbour algorithm is very similar to Prim's algorithm of how that works. Now, it's very similar, they're easy to get confused, and some people, when they're actually doing Prims, the way that they get it wrong is that they are actually doing the nearest neighbour algorithm instead. And I'll show you what I mean. So Prim starts off, choose any vertex, and in this case, okay, we will start with A. Okay, so I'll just write the letters in first. So that's A, B, C, D, and E. Okay. Now, say we're going to start at A. You will be told which vertex to start at, okay, in the exam. But the method will work starting at any vertex, okay, just like Prim's did. So first off, I'm going to take the shortest edge going out of A, and that is 1. Then I look at B. Okay, with Prims I would have looked at both vertices A and B now, but instead I have travelled from A to B, so now I am at vertex B. I'm looking for the shortest edge out of B that doesn't connect a vertex that I've already visited. Okay, so the next one is BC. So from C, I'm now looking at the shortest distance to get to either E or D, and that will be E. And now I'm looking at E and the shortest distance from E to D. Okay. By shortest distance here, I'm meaning the edge that connects straight to it. Okay, so I'm not looking at using Dijkstra's algorithm to figure out the quickest route from E to D, because it needs to be a Hamiltonian cycle, so vertices don't get repeated. And then from D I need to go straight back to A. Okay, so our route in this case was A, B, C, E, D, A, and that is our Hamiltonian cycle, and that has a total weight of 1, 2, 3, 4, 8, 11. Okay? So the nearest neighbour algorithm has given us an upper bound of 11. So the optimal solution, okay, our optimal solution for this problem, sorry, I'll put it on pen, is greater than or equal to 8, Okay, so I'll put optimal. Which is less than or equal to 11. Sorry, quick check there. Didn't want to write down the wrong number. Okay, so our solution is between 8 and 11. The lower bound algorithm has given us a definite lower bound. The Hamiltonian cycle of value 8 may not exist. Okay, it may not. But we'll definitely not be able to find one that is less than 8. Likewise, our best solution will be below 11. So it's in this gap, and we can't say for certain where it is, or of what value it is. Okay, so this is the travelling salesperson problem. There are ways to improve these bounds, these lower and upper bounds, okay, so the distance between them is minimized, but the tool improvement algorithm that is found in the book we don't need to look at for this exam, but you should be aware that those kind of algorithms are out there and can be used.